19, quiz 1. So here we go with chapter 19. Chapter 19 is basically kinetic theory of matter, which is fundamental. This is chapter 19 is the first chapter we have in this course where we actually look at the universe from a microscopic point of view, from a microscopic physical point of view. I've used the term microscopic a lot when I talk about integral and differential calculus, because that's, dealing with the infinitesimally small time steps or deltas. Here, though, we actually take a look at the physical world itself from a microscopic perspective, literally at the atomic and molecular level. So if you haven't watched the chapter 19 green sheets, boy, you have a lot of fun ahead of you. I mean, really, though, I don't know if fun's the right word, but the chapter 19 green sheet lecture video really goes into a lot of background story, very fundamental. What is pressure? What is internal energy? What is temperature? All of that good stuff. So I might touch on a lot of those fundamental concepts as I go through these problems, but I'm going to leave the really long-winded rants for those lecture videos, and you should take advantage of those. Right now, we're looking at an ideal gas. So one of the problem-solving techniques that I keep stressing is read the problem statements over and over again and incessantly. I mean, I've learned that just myself, is a lot of times just reading the problem statement many times reveals stuff, kind of maybe reveals hidden messages or starts your thought process. Here's one: ideal gas. So as soon as you see this term ideal gas, there's a little trigger that goes off and says PV equals nRT. This probably is not the first time you've seen PV equals nRT, the ideal gas law, also known as PIV-NERT. Most of you have had this in a prior class. Most of you have had this in a prior chemistry class, most likely, but maybe not. And if you haven't, this is the ideal gas law. It relates pressure, volume, amount of material, which in this case, we're kind of focused exclusively on gases, with maybe a couple of exceptions. But from chapter 19 and chapter 20, with some exceptions, is predominantly focused on gases. Remember the big picture here. We're talking about thermodynamics, which is heat flow. And for us, it really means, hey, what's going on when heat flows between two regions at a different temperature? And it has profound meanings, both practical and very exotic. Everything from a lawnmower's efficiency to the heat death of the universe and creationism versus all of that conversation. So this PV equals nRT is the Swiss Army knife. I refer to this a lot. And in case you don't know what a Swiss Army knife is, there's a Swiss Army knife. So a Swiss Army knife basically does everything. It's one package that contains a whole bunch of tools to deal with whatever situation you find yourself in. And that's why I'm always referring to the ideal gas law as the Swiss Army knife of thermodynamics, because it's kind of used universally, or it's a very foundational equation, the ideal gas law. And there's a few stipulations. A gas needs to meet certain criteria to qualify as an ideal gas law. All the collisions need to be elastic. The density isn't so great that you have intermolecular or covalent cloud interactions. So anyway, I'm not going to go into those now. I'm just going to whet your appetite for the chapter 19 lecture video. I'm going to mostly just focus on applications here. And you will be, to be honest, you will be kind of shortchanged if you just focus on applications and you don't dive into the background conceptual underpinnings. It's not going to be as good as it could be. You are going to believe you will kind of rob yourself of an opportunity to learn deeper than you otherwise would. So this is an ideal gas law. PV equals nRT is in play. It's taking through a cyclic process. I'm thinking cyclic process. That's a trigger for me too. Cyclic process means delta state variables. If it's a cyclic process, the change in all state variables equals 0. And then that begs the question, what's a state variable? Here are the state variables. The state variables means path independent. State variables means if I'm a state variable, I don't care how I got to be what I am now. All I care is what am I now? Whereas if I were a path dependent variable, I would actually care, like, what happened to make me the person I am today? A harsh upbringing. No, I'm just kidding. So here are the state variables. Internal energy is a state variable. Pressure, volume, temperature, entropy. There's one more called, I'll leave it at that. These are good right now. 1, 2, 3, 4, 5. So these are the 5 state variables. There's 5 state variables, meaning, again, they don't care about their history. They only care about their value right now at this location, at this point in time, as contrasted with path variables. Path variables, once again, care about their lineage. They care about the path that led them to where they are now. And the path variables are heat and work. Path-dependent variables, path-independent variables, also known as state variables. So if I'm starting off here at thermodynamic energy state A and I end up at thermodynamic energy state A, nothing changes in terms of pressure, volume, temperature, and entropy. However, there has to be a change in terms of Q and W, in terms of heat and work. There's no way you can go through a cycle without having some amount of heat and work produced or consumed. All right, so having said that, we're given this graph, yet another PV diagram. PV diagram, you're going to see thousands of PV diagrams. And then the question is, knowing what we know, how many moles are in the sample? So let's just start. Ready? Number 1, part A is saying, well, let's figure out how much stuff is in this sample. And by stuff, I mean how much gas is in the balloon, or probably what I'm going to start doing. I'm going to start doing, let me see if maybe I'll keep referring to a balloon. I'm looking for a graphic. I'll keep going here. There is something known, and you're going to be using this, I think, well, you're going to be using this a week from Thursday. I'm going to start referring to this cylinder. So let me draw a cylinder which contains our working substance. Working substance, again, means what kind of gas? What is it doing the work? Is it a cup of water, or is it a mixture of gas and air, or is it just helium, or so on and so forth? So what I'm going to do here, I'm going to actually just start really leaning on this as a reference. I'm drawing a cylinder, and then inside this cylinder, I'm going to draw a movable piston. And I've showed you this in the class. You're going to be using these a lot more in terms of real live laboratories. So I'm doing my best to draw a piston, and this piston can slide up and down within that cylinder, which is no mean feat, because what do you want? What do you want in this case? I want 2 things. I want this to be an airtight seal. So I want the working substance that's trapped right here. So let's just pretend there's a whole bunch of air molecules. Let me just draw air molecules. These little dots, they're molecules of air. And air is a mixture of nitrogen and oxygen, and there's traces of argon and carbon dioxide. But these little green dots are representing the working substance. This is the gas that will be doing work. And what I want out of this cylinder with piston is I want it to be airtight. So again, this is quite the challenge. I want no air to escape. So I'm just going to write down, I want this to be airtight, which means no air flows in, no air comes out. And then here's the opposite end. This is the real challenge. I want it to be airtight. And when this piston moves, I want it to be frictionless. So that's the hard part. How do you have a frictionless piston within a cylinder able to maintain air tightness? And the answer is, well, look at your automotive engine, or again, a lawnmower engine. Internal combustion engines, like again, your automobile, your lawnmower, your bus, your truck, whatever vehicle relies on an internal combustion engine, they have pistons and cylinders that do exactly this, which is why oil is so important, which is why engines cost a lot of money, because they're very precisely machined, very high tolerances. And I'll say more about that. But anyway, that gets us going. Because N is referring to the amount of stuff in this enclosed system. And specifically, the enclosed system is what I'm highlighting here. This is the enclosed system. It's a confined volume of working substance. So how much working substance is in this system? And the answer in this case is $. This is what we're after. I was going to blurt out a number, but in this case, that's what we're looking for. We're looking for the amount of working substance. Is probably the safest way to put it. You could say the amount of working gas, but it's not always a gas, but it's typically, I just like to use the word working substance because it could be air, carbon dioxide, it could be hydrogen, it could be anything. All right, so that's number one. Number one is part A. How many moles are in this sample? And I'm going to say seems like a job for the ideal gas law, also known as the Swiss Army knife of physics, because more often than not, you're going to have to lean on the ideal gas law because it's fundamental. And one thing I'll start mentioning about the ideal gas law is it's assuming the basis for it is absolute zero. So try to make a big deal about that incessantly in the Chapter 19 lecture video. But it does. I mention that because it helps, I think, keep your head clear. Like when can I use Celsius? When can I use Kelvin? And let me write this down, I think, for the 7th time, because I think it's helpful. It's very helpful to me. I like to always remember 1 Kelvin does equal 1 Celsius degree, but 1 Kelvin does not equal 1 degree Celsius. So if you understand that, digest it, it's gonna keep you out of trouble in terms of incorrectly using one scale over another. Okay, so let's keep going with figuring out how much material do I have in this enclosed system. Number 3. Well, seems like a job for the ideal gas law. The ideal gas law is PV equals nRT. So could it be this simple? Because all I need to do is N, just rearrange. If PV equals nRT, then N equals PV all over RT. So let's go with that. So N equals pressure. N equals well, here, you know what I'm going to do? I'm going to do this because I do have a lot of choices. I have 3 thermodynamic states. I have A, B, and C. And I want to make sure I have enough variables. Like, what do I know? I know it's an ideal gas. I know the pressure at B. So this pressure at B, for me, these are my numbers. You have different numbers. The pressure at B is 9170 pascals. What else do I know? PAC. So the pressure at A apparently is the same as the pressure at C because it's referred to as PAC. This is 6820 pascals. At point A, at thermodynamic state A, I do know this temperature. This temperature is given as the temperature at A is 196 Kelvin. What else do I? And that's kind of it. So that steers me in a direction. I'm going to stick with N equals PV over RT, but I'm going to subscript things. So this is pressure at A, volume at A, all over R, which is a constant, so I don't need to subscript that, all over T, subscript A. There it is. So far, this is very rudimentary. This is really just solving for N in the ideal gas law equation. But actually, the hard part now is going to be units. So let's see. What is my pressure at energy state A? My pressure at energy state A is the same as the pressure at energy state C, because it's, again, it's shown as a flat line. So I know this is isobaric. I know that's an isobaric process because the pressure remains the same. Iso means same, baric means pressure. So I do know my pressure at A. It's 6820 pascals. And this is where I would normally say you absolutely know what a pascal is because you've watched and digested the chapter 19 green sheet lecture video. But again, because I didn't make it, I may not have made it super clear that that video link was available. You know, it's been available all the time. Maybe I'll say a few words about the pascal, and I do want to maybe just go back for any late arrivals and just for reinforcement purposes to say, hey, look at your class web page. If you look at your class web page, it's been updated to include this link, the YouTube green sheet lecture videos. So you have access right now. You have access to the entire set of YouTube lecture videos that accompany your green sheets for every unit in Physics 212. And let me make sure I'm sharing what I think I am. All right, so there. All right, so a pascal is a definitional unit. A pascal is a Newton per square meter. Okay. And you actually, well, a little sidebar on Pascal. 1 PA means 1 Pascal. 1 Pascal is defined as 1 Newton per square meter. And what is a Newton? A Newton is a unit of force. A square unit is a unit of area. And you should recognize force per area. Force per area is defined as pressure. So there's a little quick backlog or backtrack on what a Pascal is. So that's what a Pascal is. Now I need to multiply it by, what is my volume at A? Do I know my volume at A? Assume VA, I do, it's given. It's given here. I do know my volume at A. So let me erase this. Okay. Assume the volume at A is 1.55 cubic meters. 1.55 cubic meters. All right, that's my numerator. Here's my denominator. R is the gas law constant. 8.31 joules per mole times Kelvin. This is one of the very most fundamental constants in nature. It's called the gas constant, and it's just basically determined. Basically, you hire a bunch of lab technicians and you tell them how to systematically vary this piston. So this would be, we could do this in a lab. You know, we could say, okay, today class, we're going to spend a few hours looking at this setup, and we're just going to systematically vary everything and figure out how it's all related. And at the end of the day, you're going to say, well, this is what I figured out. I've done a whole bunch of lab activities. And at the end of the day, I have discovered, or I now see, that PV is proportional to NT. So this fish, it looks like a fish. It's a proportionality constant. And we could do this. We could do this in less than 3 hours. We would very quickly be able to come to the realization that that this is true, that P times V is proportional to N times T. And then if you want to use an equal sign, you would say, okay, well, if PV is proportional to NT, what is that proportionality constant? And the answer is R. So if you want to go from this fish-looking symbol, which stands for proportional, to this equality, this equal sign, you can do that. Everything's the same, except now I'm introducing this gas law constant, and we'd be able to figure that out. In fact, you're going to do a simulation where you figure that out. So 8.31 joules per mole Kelvin, that is the R value. So I've taken care of P, V, R, and this is what set my direction early on. It says at point A, the temperature is 196 Kelvin. So that's why I focused on energy state A, thermodynamic energy state A, and that's why I started subscripting. There it is. We're ready to get a number. Let's get a number and then let's do dimensional analysis. Although technically speaking, we should do dimensional analysis first. Let's not get a number. Because if I do dimensional analysis and I don't get the correct units, then I would have wasted time getting a number. So, and you're going to do this on the exam. Let's do dimensional analysis. In my numerator, I have a Pascal. A Pascal is a Newton per meter squared. That's a Pascal. It comes from the definition of pressure, force per area. Then I have also in my numerator, I have meters cubed, because we express volume in terms of cubic meters. And in my denominator, my units are joules, mole, Kelvin, okay, and then times Kelvin. So again, I'm spending a good amount of time on dimensional analysis because you're going to have to do it as well. And it's not a penalty, it's a good thing to do. So here's Kelvin, and then Kelvin cancels with that Kelvin. And then, so you know what I guess I'm looking at now. The drama continues. Upstairs, I have Newton meters cubed all over meters squared. That's my upstairs. And then downstairs, I'm just left with joules per mole. So there's more. The intrigue continues. If I can see, well, I can certainly see how this cubic goes away because squared meters. If I divide cubic meters by squared meters, I just get meters. And I remember that a Newton times a meter is a joule. So now upstairs, I have a joule. Downstairs, I have a joule per mole. It should be MOL, not M. And so I'm feeling good. This is time well spent. And in fact, this is time that should be spent before you go to your calculator. Because again, if I ended up with the wrong units, you just have wasted all that calculator time. But I'm ending up with moles. So good news. I'm going to end up with moles, which is a cause for confidence. Now I just got to get the right number. 6820 times 1.55 divided by 8.31 divided by 196 is 6 point something. Hang on. Let me and I better store this in my calculator memory. So number four, I have N equals 6.49, but there's more to it. It's 6.49021. I mean, you have different numbers, but we have lots of numbers to the right of the decimal place. Let's not sig fig things just yet. Let's keep all this precision. Let's include the units and include store in calculator memory location A. Okay, so store alpha A. So we now know, we know how much working substance is in this piston. We just figured that out. That's part A. We are done with part A. We now know how much material is right here. I'm just highlighting it on your screen. I want to make sure everything is making sense. In my case, I have 6.49 moles of stuff within my enclosed system. Think of this as a piston in your car or lawnmower. All right, so that's part A. Part B says, what's the temperature of the gas at point B? This might be kind of quick, but good opportunity for me just to really reinforce the basics, which I'm doing right now. So what's the temperature? So T subscript B is the dollar sign. That's what we're looking for in part B. And let me highlight that. This is part A. All right, so this is our answer to part A. Part B is how much, or what's the temperature at energy state B? So I'm focusing my attention right here. What is that temperature right here? Okay, well, this seems like a job for the ideal gas law, I think. And if it's not, we'll react to it. But I'm thinking ideal gas law again. So let's go with that. PV equals nRT, and this was derived through systematic experimentation, and the temperature scale was absolute zero, the Kelvin temperature scale. So then I'm going to do this. I'm going to isolate and subscript the temperature at thermodynamic state B, therefore must equal the pressure at B, volume at B, all over N. And I don't have to subscript N because we're assuming it's a closed system, which means no material enters or leaves, over R. Okay, so let's just run with that and deal with the units. The temperature at B is going to equal the pressure at B. The pressure at B is given. The pressure at B is given to us as 9170. My number's not yours. Pascals. So there is P. Here's V. What's the volume at B? It's given. The volume at B is also stated in the problem as, I'm just erasing this, 4.94 cubic meters. 4.94 cubic meters. There's my numerator. Here's my denominator. I'm just gonna write down calculator memory location A. That's N. The number of moles is 6.492, and this is why it would be a mistake if you sig fig-ized this number and you entered or you used the sig fig version of that. That's technically incorrect. All right, so I'm just going to refer to the memory location. I'm going to drag along the units. Units are critically important. There's the N and here's the R. 8.31 joules per mole times Kelvin. Dimensional analysis, it's the same. Well, no, it's not the same. It's not the same. So I'm going to do the dimensional analysis. As far as dimensional analysis, and it would be a mistake for you not to do dimensional analysis first. All right, so I know a Pascal is a Newton per square meter. I know I'm multiplying that by cubic meters. That's my upstairs. My downstairs is moles times joules per mole. So things are different here, K. And from there, once again, my upstairs, if I have cubic meters divided by square meters, it's just meters. So here's my new numerator. And I know a Newton times a meter is a joule. Here's my new denominator, joule per Kelvin. So I have a joule over a joule per Kelvin, or Kelvin. So I am getting Kelvin. Now it makes sense to go to the calculator. 9170 times 4.94 divided by alpha A. Okay. 839. Number 6, number 7. I'll go over here. Number 7. The temperature at B for me, 839 and some change. 839.9 Kelvin for sure. Store that. SICM means store in calculator memory location. For me, I'll call it B. So store alpha B. Done with B, part B. Seems pretty easy so far. Definitely an ideal gas law exercise. See, what is the temperature? All right, so I think what's the temperature of the gas at C? So you know what? Let's kind of work independent. Well, I'll talk through this, but I can go quickly through this because it's very familiar to us. Let me just highlight this. So this actually was the answer to part B. That's the answer to part B is now known, stored in my calculator memory. And then so again, this is just an exercise in applying the ideal gas law. Now part C wants you to do the same thing for the temperature at thermodynamic energy state C. So let me just kind of cruise through this at maybe a little bit higher velocity. PV equals nRT means T equals PV over nR. And with subscripts, the temperature at C is equal to the pressure at C times the volume at C all over N. Don't need to subscript N, all over the ideal gas law constant. And my pressure at C is the same as the pressure at A, isobaric. And for me, that's 6820. And you know what I'm going to do? Instead of writing a Pascal, I'm just going to go right to newtons per square meter, just because I'm bold like that. Volume at C is given as 4.94 cubic meters, 4.94 cubic meters. That's my numerator. N is still in calculator memory location A. Units are moles. R is still 8.31 joules per mole Kelvin. So I'll leave it to you. For sure, you should do the dimensional analysis and make sure that you do get Kelvin out of all of this. 6820 times 4.94 divided by alpha A divided by 8.31. Okay, 624. 624 and some change. That's the answer to part C. For sure, store this in your calculator memory. Okay. 3 down, 1 to go. Nothing too challenging thus far, but maybe let's check out part D. Although there is a lot to say. Once we're done with this, we need to talk about some essential points. What is the net energy added to the gas as heat? Well, that's something. This is definitely new and more advanced. Okay, we need to figure out how much energy got added to the gas as heat. So let me scroll, I guess. Let me shrink. So now we're in the realm of the first law. Parts A, B, and C was all about applying ideal gas law, which is good, but I'm gonna use a special blue color for changing gears. So again, part D part D says, what is the net energy added as heat during the cycle? So I'm just gonna write that as Q. Maybe I'll do it like this: Q from A to B to C to A. That's what we're after. That's the net amount of heat, net amount of heat added to this. And again, you know, heat's been added because why do we like engines? Because they do work for us. What price do you pay to get that work? You pay in the form of heat. Where does that heat come from? Your spark plugs. Your spark plug makes a little spark, and then all of this internal working substance right here blows up, basically. And again, much more said about that in the lecture video. And I'll say a lot more on Thursday as well in terms of demonstrations. But we're after part D. How much heat did you need to invest to get this amount of work done? So number 10 says, seems like a first law situation. Seems like a first. And why am I saying it seems like a first law situation? Why am I not saying it seems like an ideal gas law situation? And the only reason is two reasons. Because I have a closed cycle, number one, and I have a what else makes me think of the first law? Closed cycle, and I need heat, and I need to find heat, All right. So that's my way of sort of looking towards the first law of thermodynamics. Here's the first law of thermodynamics. Change in internal energy equals Q minus W. So it's just a balancing act. The amount of internal energy you have in a system depends on how much heat you add or remove, and it depends on how much work is done on the system or by the system. And that is, again, another big deal. I try to really underscore repetitively. What do those two terms mean? What is the difference between work done on a system versus work done by a system? So very fundamental stuff. But right now, this is what I was thinking. You know why? Because for a closed system, there is no change in any thermodynamic properties. So in a closed system, we have 1, 2, 3, 4, 5 variables that remain unchanged. So for a closed system, there is no change in internal energy. So that equals 0. That's why I'm thinking of the first law, because now if I update number 11, if I look back at number 11, I now have 0 equals Q minus W, or Q equals W. So that's major. Aha. So I'm writing aha down because this, I can find W. And you might think, well, can't you find Q? Well, I am trying to find Q. So I guess that was maybe not the question I would ask myself at this point, but I can find W. I can find W for this system because this goes back fundamental. I know that work is the integral of PdV. How do I know that? Because it was derived in tremendous detail in the Green Sheet lecture video, chapter, was this chapter 19? This might have been chapter 18. In chapter 18 or chapter 19, this was derived very, I think, very thoroughly. And just for those of you who remember about what work is, you remember work. Work is basically force times distance. I think a lot of people were taught in middle school, then maybe again in high school, and certainly here at the college level, high school level, you're taught very many times that work is force times distance. And to be maybe even more precise or a little more rigorous, work is the dot product of force and displacement. So, but you can actually get away saying work is still force times distance. Just be careful how you actually calculate that analytically. And then you might remember, well, I remember force is Newton's second law is mass times acceleration. So anyway, there's a whole chain. Well, you could even say here, I'm going to just stop myself there because again, all I'm doing is just repeating the Green Sheet lecture mode. I'll leave it here just in the interest of time. And once again, say I'm in a good mood because I do know that work is given by the integral of PdV. And I know that the chapter 19 lecture video, maybe it was chapter 18, maybe both, but I know that the backstory here is essentially important. You have to know the backstory. You can't just write down equations and plug numbers into the equations. If you are, jump off the scientific and engineering path, because the scientific and engineering path means you actually do understand the derivations, because that does make you a deeper thinker. It does. It just does. So now the ideas are flowing. More ideas. If I'm going to go back to my PV diagram, I know from the fundamental theorem of calculus, part B, the fundamental theorem of calculus. So whether or not you know that term, whether or not you know, when I say fundamental theorem of calculus part B, maybe you recognize that term, maybe you don't. But what you do know is the area under this graph right here. If I'm just going to highlight this, check out this little annotation I'm doing here. This area under the graph from A to B. So if I go from state A, which is right here, if my system is proceeding from thermodynamic energy state A to thermodynamic energy state B, going in this direction like that, I know some positive work is done. So if I'm going from A to B, I know my volume is increasing. Volume increases. So my volume increases from A to B. If my volume increases from A to B, it means I'm doing positive work. Work is greater than zero. It's not equal to zero. It's not less than zero. It's greater than zero because my volume going from A to B is increasing. It would be literally as if I'm taking this piston right here, this movable piston, movable yet friction-free. It would be exactly the same as if I'm moving this piston from some lower height to some higher height, higher position. If I move this piston from a low position to a high position, not an incredibly good drawing, but if I do move this piston upwards, my volume is increasing and positive work is being done. Okay, so you know from calculus that the area under the path from A to B is what I'm indicating here in this with these gray shaded marks. So I am cross-hatching the area under the path from state A to state B. So whatever this shaded area is equivalent to, whatever the size of that shaded area is, that equals this. The integral of PDV is the area under the curve. You guys know that from your calculus test. Area under, right on area under.
Professor Woods?
Yep.
Can you reopen the quiz?
Yeah, I will. I will do that. Okay. So back to it. The area under this crosshatch gray area that I've indicated corresponds to the integral of PDV. So area under curve is how I think we normally say that. And specifically, it's area under the curve from A to B. Now, however, there's a however here, because we're not talking about the question didn't ask us to figure out what's happening from A to B. The question asked us, what's the net amount of heat added from A to B to C back to A? So number 15, this is positive work. So from, I'll write it like this. Check this out. The work from A to B is positive because the volume's increasing. The work from B to C is equal to zero. That's isochoric. It's not that the force is zero, but there's no change in volume. If nothing moves, then there's no work done, even if the forces are not equal to zero. The work from C to A is less than zero. Why am I saying that? First of all, the work from C to A, this is isobaric. This is isobaric work, and the volume's decreasing. Isobaric work. And I'm saying it's decreasing because if you look at this graph right here, if you look at your PV diagram, you're going from energy state C to energy state A, which represents a contraction. So let me just show it right here. I'm going from C to A. My piston is moving down because my volume's decreasing. That's negative work. And I guess that's it. Okay. So let me just check that. From A to B, yes, positive work. You are for sure the case. From B to C, there's no work done. That's an isochoric process. From C to A, that's an isobaric process. Negative work done. All right, so now I'm going to do the same thing. How much negative work just happened? Here's how much negative work just happened. This much negative work. Let me change colors. This much negative work from C to A. The answer is it's the area under the graph. So I'm saying that again. It's the area under the graph from C to A. Let me crosshatch this. So what I'm crosshatching here in green, that's negative work. And remember, the positive work was crosshatched in gray. I'll put that back. From A to B produced all of this positive work. And you can see this overlap. You can see I have gray and green kind of overlapping each other. So gray was positive work, green is negative work. So my net amount of work is right here. This is the net work done from A to B, B to C, C to A. This is my net work done, this crosshatch area right here. Because basically red equals gray minus green. And you know what that is? That's a triangle. So it gets a little bit anticlimactic, but the work done, the net work done for this entire closed loop circle is now boiling down to be given by the area of that triangle. So I know that for the area of a triangle is 1/2 base times altitude. So specifically, I could say that the integral of PDV is equal to 1/2 times the base. What's the base of that? What is the base of this triangle? The base of this triangle is whatever VBC minus VA is. That's the base of my triangle. What's the height of the triangle? The height of the triangle is PB minus PAC. All right. So again, let me just stress this. I'm after this red triangle. I'm trying to figure out the area under that red triangle for all the aforementioned reasons. So let's do that. What is 1/2? I'll do it like this. So the work, I'll write like the net work done is equal to 1/2 times VBC, which for my numbers, that was given as 4.94 minus VA. VA was also given 1.55. They shared the common units of cubic meters, which is the unit of volume. So I'm just going to pull it out as a common factor, times the pressure difference. The pressure at B, was given, wasn't it? Yeah, 9170. 9170 minus the pressure at A, which is the same as the pressure at C, which is why it's called PAC, isobaric, which is given as 6820. 6820. And they share a common unit of a Pascal. And again, whenever I read Pascal, I'm just going to go right to newtons per square meter. That is the net amount of work done, which should also equal the net amount of heat added, which I wrote down originally as the amount of heat added from A to B to C back to A. Okay, so let's just dimensional analysis. What do you get? What do you get if you take a cubic meter and multiply it by a Newton per square meter? So this is the dimensional analysis part. You get a Newton times meter, which a Newton times a meter is a joule. And I do expect joules. So dimensions I'm feeling good about. 0.5 times 4.94. Okay. $39.83. Okay. And we're done. My calculator says 39.83.25 joules, and that's the answer to part D. And believe it or not, there's actually more we have to say about this. So this is we're spending, when it's all said and done, we're going to spend more than 1 hour on one problem. And it's time well spent. And I could spend a lot more if I wanted to go into all of the green sheet lecture background story, but no, you need to do that. Okay. One thing, one thing I have to highlight here. Let me just grab a picture from somewhere. This is 1913. So you keep working. If you're still finishing up, I'm going to grab a picture. There. Okay. So I'm kind of taking my time getting this picture because I'm just making sure no one's feeling rushed. But I will come back and actually stress the following point. This was the PV diagram we were working with. This is one thing I need to start stressing now. Sort of excerpting from the lecture video. We figured out the temperature at point A. With my numbers, the temperature at energy state A, what was given. So with my numbers, this was given as 196. So this was 196 Kelvin. And then we went through and calculated the energy at B and C. So for me, the energy at B was 840, about 840. So I'm going to label this as 840 Kelvin. And also with my numbers, the energy at state C was given as 625. So again, I'm spending all of this time for a reason. Because you need to get to the point where you understand how and why the temperature at B must be greater than the temperature at C, must be greater than the temperature at A. The goal is just to be able to look at these three temperatures and say, well, I might not know what they are numerically off the top of my head, but I know that temperature at B is greater than the temperature at C, and the temperature at C is greater than the temperature at A. And that's because you can tell from here, they sit on certain isotherms. There's the isotherm for B. There's the isotherm for C. There's the isotherm for A. So I'm going to write this as here. This is the TB. This is the TB isotherm as an isothermal. This is the TC isotherm, as in the isotherm, the constant temperature at state C, and this is the TA isotherm. And you can see now when you just draw these isotherms, and you know isotherms are always hyperbolic. Isotherms are always given by that hyperbolic shape or that inverse shape. Because if PV equals nRT, you can say T, therefore, or I'll write it like this. If PV equals nRT, you can say P equals nR over V times T. Okay. And that's how you're seeing this hyperbolic relationship between pressure and volume, between pressure and volume. You can see that they're inverses of each other. So these are inverse curves. So again, hopefully within the very foreseeable future, you would look at a diagram like this and you say, again, I don't know what the numerical values are at A, B, or C, but I can see how B is sitting at a higher isotherm compared to C, and C is sitting at a higher isotherm compared to A. And the bottom line here is anytime you have any kind of upward or rightward progression, and any combination of up and to the right. So here's up and to the right. Anytime you progress at all upward or at all rightward, you're going from a lower isotherm to a higher isotherm. All right, so I just wanted to stress that. If that's going a little bit fast, I understand. If it's not incredibly clear, it will be, especially after you go through the video, the lecture video. But let's do one more problem. And maybe I need to kind of start picking up the pace. I'm going to unleash chapter 9, quiz 2, and then maybe we'll get through this in the foreseeable future so we can take a much needed break and start getting some more problems done. Chapter 19, quiz 2. It's now about 9:03. 9:03, chapter 19, quiz 2. Okay. All right. Chapter 19 quiz 2 should now be available. Please let me know if it's not. And it should look like this. Okay. Let me get rid of my scribbles. Okay, this is changing gears a bit. This is a relatively different type of problem. It's thermodynamics. So you could say, hey, Chris, how different is it? It's still thermodynamics. But within the realm of thermodynamics, it's different in that this is not an ideal gas law situation. This is not an ideal gas. So that's the first thing that jumps out to me. And there goes my security blanket, because again, the Swiss Army knife of thermodynamics is the ideal gas law. And right away I'm saying this is not an ideal gas. It's not an ideal gas because an ideal gas, once again, the ideal gas law, IGL, says PV equals nRT. That's not what we have here. This is not PV equals nRT. This is some special, or this is some different relationship between pressure and volume, not PV. And then you would ask yourself, how do you make that happen? And the answer is engineering. You would basically just chemical engineer or mechanical engineer your way into finding a combination of, reactors and pumps and vacuums and so forth that basically cause this gas to behave according to this polynomial function right here. So it's not an ideal gas law. The question is, if you're dealing with this working substance, whatever it is, they say certain material. So the certain material is the working substance. Find out the work done. So that is a very key term. Knowing what you know about this situation, what is the work done? So pressure P, volume V, and temperature T for a certain material are related by this, which again is not the ideal gas law, but they are related at least, where A and B are constants. A has a value of 349 with some units. B has a value of 0.131. And then your job is to find out the work done by the material. They use the word material. It's referring to working substance. If we have a delta T, if we go from a low temperature to a high temperature, this is another keyword. It's an isobaric process. While the pressure remains constant. Pressure remains constant means this is an isobaric process. I don't know if I need that, but it's good to shout it out. This is an isobaric process because the pressure is remaining constant. All right, so this is not an ideal gas law, but I'm going to fall back on the following. I know this was derived. That work, and I'm going to just use this triple equal sign here just to remind everyone, this was a derived definition. Or I'm sorry, It's good that I said that out loud. It was not a derived, it was derived, not a definition, sorry. So the work done by a gas is the area of PdV. And yes, it equals the area under a curve, but I don't have any kind of graphical information here. So you know what I'm going to do? I'm going to take a calculus approach. Need calculus because I don't have an alternative. I'm not given a graph like I was in the last problem. So I'm going to start here. I know it's given P equals A, which is some constant, times T, which is my independent variable, over volume minus BT squared. So I'm just writing this down. I'm just sort of copying and pasting this expression. And this is step 4, not step 7. All right, so I guess here's my thought process. I am still very much focused on this expression for work. It's not enough definition. We derive this. All right, so because I need to figure out the integral of PdV, I guess my next move here is to multiply through by volume. If I multiply the right side through by volume, it means I must multiply the left side through by volume. And if I multiply through everything by volume, then I have P times V equals AT minus BT squared. And my whole motivation to do that was to get need to get to this form. I need to get to integral of PdV. That's what I need to get. So I don't have the integral of PdV. I don't even have PdV. I just have PV. So I'm going to do this. Pressure is constant. Here's my way of writing pressure is constant. Just a nice shorthand way. Delta P equals 0 means pressure is constant. It says, find how much work happens during this process if the pressure remains constant. This is, again, how I'm going to say pressure remains constant. So I'm going to take the derivative of both sides. Take derivative. Differentiate both sides. Take derivative of equation number 5. If I take the derivative of equation number 5 and pressure is a constant, I have P dV equals A dt. Just differentiate. I am differentiating every term minus 2B T dt. That's it. And why am I liking that? Because this is my PdV. So now with number 8, I'm just going to integrate because I got myself to that point where I have PdV, which my motivation was that's the expression for work. Integrate. So if I integrate both sides, I'm going to have the expression for work. So all I'm going to do is slap an integral symbol here and an integral symbol here. And if I have that, then I can say number 10, work, which is the integral of PdV, is equal to the integral of all of this, A dt minus 2B T dt from some lower bound, some initial temperature, which I know it's given in the problem statement, to some final temperature. All right. So the work done by this non-ideal gas is, I can do this, I think. I know that the integral of A dt is just AT. And I know that the integral of 2BT is, so here's me doing just power rule integrating BT squared. There you go. I'm starting off at 255 Kelvin. And I'm ending up at 292 Kelvin. And let's see. Do I know A? Do I know Yeah, A is given. And I'm going to do the dimensional analysis. And when I say A, I guess at this point, I'm going to say you. You need to do the dimensional analysis because you do know the value of A. You do, for me, it's 349 joules per Kelvin. You do know the value of B. For me, it's 0.131. I'm sure your numbers are quite different. The units are given, which is good for dimensional analysis. And go ahead. You can now finish. So let's see. Number 12. So you're going to get some number. And it is now 9:13. Let us resume. I will see you guys. Is 10 minutes enough or too much? I'll see you guys at 9:24. See you at 9:24 a.m. So finish this problem. Feel free to talk amongst yourselves if you need help with the calculus part here. Let me know if you see any mistakes, and we'll catch up. But for right now, I'll see you guys at 9:24 p.m. to start quiz 3. 9. And we're back. As I look at the grade book, let's see how everyone's doing this for the 2 quizzes we've had thus far, chapter 19, quiz 1 and quiz 2. Wait for it. Pretty much everyone is done. I suspect if you're not done with quiz 2, I mean, here's my guess. Happy to admit a wrong guess, but my guess is if you haven't finished part 2, you haven't had calculus. You either haven't had calculus or you're just very, very rusty with calculus, which is totally cool. I know what it's like to take a prerequisite and then discover that my prerequisite skills are quite forgotten or quite I need a lot of refresh. So I'm just this public service announcement. If you haven't had calculus before, which is a prerequisite for this class, that's an issue. And I would advise against it. Again, if you were going to become a medical doctor, I would advise that you take biology before you take human anatomy for kind of the same reasons. But on the other hand, if you just need a refresh, which is very probable too, that happens to me a lot, reach out to me. I can give you a refresh that is very much consistent with our book here. It's a refresh brought to you by the publisher, the author of this book, a calculus refresh. So if you need, let me take my mute off for a second. Just let me know if you can. And I keep saying, let me know if you can't, because Wiley Plus has been undergoing quite a few changes recently. And a lot of times when I think something is available, it's not. So that's why I seem to be extra careful and saying, please let me know if you don't see this assignment. But I'm seeing this assignment. So now we change gears again. So I'm moving through chapter 19 almost, at great speed, or it would seem to you like I'm hopscotching through chapter 19, taking giant steps. But it won't once you review that lecture video, fill in your green sheets and review this Zoom lecture. And again, you guys all hopefully know to log into Blackboard and to access these recordings via Blackboard, which I would do a lot as well. Let's start this. Let's start chapter 19, quiz 3. The first thing I'm going to do is show an incredibly exciting video called The 6 Degrees of Freedom. And let me get this set up. 1980s soundtrack video game sounds. But anyway, here, let me do the following. Okay, let me make sure I'm sharing the way I think I should be sharing. Okay, now check this. I'm going to show this a whole bunch of times. It's short and sweet. On credit to where credit is due, Enrique Zeleny. All right, that's 1 degree of freedom. So let me stop here. Let's pretend we have a diatomic molecule like oxygen gas, O2, or hydrogen gas, H2, or nitrogen gas, N2, any of the diatomic gases. A lot of gases occur naturally as two atoms. So we're looking at a diatomic molecule here. Let's just say, for the sake of conversation, you're looking at an oxygen molecule. And now we're going to count up the degrees of freedom that a diatomic molecule has. And it doesn't matter. It doesn't matter if it's oxygen or nitrogen or fluorine or anything. It just has to be a two-atom molecule, also known as a diatomic molecule. Well, let's just do a counting game first. Ready, set, go. And begin. That's one translational degree of freedom.
Your screen is just black for me.
Was it black for everyone else's? Was anyone able to see it? No, nobody was able to see it. Thumbs down. Let me try that again then. What about now? Do me a favor, unmute your mic and just let me know if you can see it.
Yeah, that's better.
Is it? Okay, good, thank you. All right, so, all right, good to know. All right, so one translational degree of freedom. Two, going in the y dimension. Three translational kinetic energy degrees of freedom. Four, spinning around that axis. Five, spinning around that axis. And six, vibrating like an accordion or a slinky. Let's watch that again. All right, ready. Diatomic, that's one translational kinetic energy degree of freedom. Two translational kinetic energy degrees of freedom. Three translational kinetic energies degrees of freedom. Here's a rotational kinetic energy degree of freedom. There's another rotational kinetic energy degree of freedom, and there's an oscillatory degree of freedom. So, having seen that video, which actually is very, with that in mind, the temperature of a certain amount of ideal diatomic gas is increased without the pressure of the gas changing. So let's just let me try to squeeze out every bit of backstory commentary out of this problem as makes sense, which means, again, a long time, but it's better. It's spending a long time now is a worthwhile investment versus just, again, plugging in numbers to some publicly available solution and not learning. I mean, how many times has this happened to you? This is happens. All right, so here you go. Let's draw a PV diagram. PV diagram done. Here's a PV diagram like that. Okay, where this is my dependent variable P and my independent variable V, and it says I have a certain amount of gas. Again, think of this piston sitting in a cylinder. Think of this example. If you're like me, you always kind of like to have some kind of physical object reminding yourself what's going on. Or think of a balloon. But it's a diatomic gas, and its temperature increases without any increase in pressure, isobaric. So this is what happens. And we should draw an arrowhead on that too. You should draw an arrowhead that looks like that. So I'm going from some initial state here to some final state here at a constant pressure, hence the term isobaric. And let's see, I know that the temperature of 3.52 moles. So there's my N. N is 3.52 moles of ideal. Ideal gas means, what does that mean? It means PV equals nRT. Diatomic gas, you just saw. You just saw what it means to be a diatomic gas. Diatomic gas means, let me draw a three-dimensional, just because this is so critical to so much of what follows. I'm just going to really try to drive home the point. Here's a three-dimensional coordinate system. If you have a diatomic gas molecule like this, ready, 1, 2. Okay, this diatomic gas molecule can move back and forth along the x dimension like this. So back and forth along the x dimension, and that represents one kinetic energy, one translational kinetic energy degree of freedom. Now, in addition to moving back and forth along that axis, this same molecule can move back and forth along that axis. So that's number 2. And similarly, it can move back and forth along this axis. Oh, hang on. Back and forth along this axis. Let me move that. So you are looking at 3. I'll put it in the center. You are looking at, so far, you're looking at 3 translational kinetic energy degrees of freedom. 1, 2, 3. And in addition to moving along those 3 axes, it can spin. So here comes number 4. Ready? It can spin like this, about this axis here. That's number 4. And then on top of that, it can actually spin about this axis here. Let me change that. Sorry. It can spin about this axis like this. And then it can also spin about this axis. And that's 5. So when you count it up, I have 3 translational kinetic energy contributions plus 2 rotational kinetic energy contributions equals 5 in total. Or I would say F equals 5 degrees of freedom. And you might say, what about that oscillatory motion? What about the situation when these 2 atoms of this diatom were basically just bouncing back and forth like they were in a like they were a slinky, or like they were attached to a spring? That only happens at ultra high temperatures. So we tend to ignore the oscillatory degree of freedom. So again, we ignore except at really high T. Because if the temperature gets crazy high, except at high temperature, if the temperature gets crazy high, then these 2 atoms will start springing back and forth, again, like a slinky. So we have 5 degrees of freedom, 3 translational corresponding to X, Y, and Z, 2 rotational about 2 of those axes. And in fact, this problem says the molecules in the gas rotate but don't oscillate. So once again, we can safely not count this as the 6 degrees of freedom. So we only have 5. X, Y, Z, and then a rotational one, and then another rotational one. Okay, so how much energy is transferred to the gas of heat as heat? Let me get rid of all of this backstory stuff. So all of that's background. All of that's just a brief thumbnail of what I talked about for probably 8 straight minutes in the lecture video. But good to get it in multiple doses, I think. All right, so part A says, how much energy is transferred to the gas as heat? So as this gas goes from some initial energy state to some final energy state, some initial state here, some final state here, at constant pressure, the only way that can happen is if you add some heat. So that's why I would call this QIF. Okay, so you dump in some heat. The piston is free to move, so the piston's going to move. The volume's going to increase, but the pressure is going to remain the same because it's just sitting there exposed to atmospheric pressure. All right, how much energy is transferred? So we're trying to find heat. Ready? For part A, Q is the $sign. And this is where I go into yet more backstory. Do you remember from chapter 18, which was last week? Everyone here remembers Q equals N, MC, sorry. Everyone here remembers Q equals MC delta T. Q equals MC delta T is is used for liquids and solids. Here's the gas version of Q equals MC delta T. Q equals NCV delta T, or Q equals NCP delta T. This is what we use if we're not working with solids or liquids, but instead working with gases, which we are here. And you know everything here, except for the following. You know Q stands for heat. Q stands for heat, yep. Delta T is the change in temperature, so that's the same everywhere here. For Q equals MC delta T, M is the amount of mass. M is the amount of liquid or solid in terms of kilograms or some mass unit. Here, though, in the world of gas, here's instead of M, we technically could use M, but it's easier to use N. N like number of moles. Okay, so that's different. And then in Q equals MC delta T, this referred to temperature stubbornness, specific heat capacity. This was the lab you guys did on Thursday, the specific heat capacity lab. So instead of lowercase c, this is uppercase CV, and this is uppercase CP. CV stands for molar specific heat capacity. So it's still a specific heat capacity, but now we say molar specific heat capacity at constant volume. Molar specific heat capacity at constant volume. And here's how I'm going to write constant volume. Delta V equals 0. Delta V equals 0 means constant volume. So it's just a nice shorthand way. CP is the same thing, but I'm going to write down molar specific heat capacity. So again, that's the same. Molar specific heat capacity at constant pressure, which I will write as delta P equals 0. So again, this is kind of, think of Q equals MC delta T for a liquid and a solid, and think of Q equals NCV delta T or Q equals NCP delta T as being used when we're working with gases. So the question for part A, how much energy is transferred to the system as heat during this process? How much energy is transferred to the gas as heat? So step number 2, this could be a job. Now, here's the question is I need to write Q equals NC delta T, but do I use a delta V like volume or delta, do I use C subscript V like volume, V for volume, or do I use C subscript P for pressure? And the answer is pressure, because pressure remains constant. Okay, so this is this molar specific heat capacity equation for a gas held at constant pressure, and that's a mouthful, but hopefully it's not too murky. It's straight, it's crystal clear after you digest it for a little bit. But let's get this answer. How much heat did I need to add here? Well, do I know N? Yes, I do know N. So I know a lot of this stuff. Here goes. The amount of heat equals N. Now here's how I'm going to write CP. CP, and this is some new introduction stuff, equals CV plus R delta T. And then I'll do delta T. I'll do T final, because we all know delta means final minus initial. So everything I'm writing down here in step 3 is a no-brainer, except for a, let's do a sidebar. There is a relationship between CV and CP. It turns out CP does in fact equal CV plus R. And if you think I'm pulling this out of thin air, well, I guess I am, but there is the derivation. The chapter 19 green sheets and the associated chapter 19 lecture video really do step this out in great detail to derive this expression. You need to understand that derivation. It makes you a better problem solver. If you understand the derivations, you're going to see the bigger picture at a deeper level. All right. But wait, there's more. There's still some more sidebar here. CV equals F over 2 times R. And remember what F stands for. F doesn't stand for final state in this case. In fact, you know what I'm going to do just to avoid that confusion? I'm going to erase this. Instead of I, because I don't want to confuse terms, I'm going to call this from some initial state A to some initial state B, which means I have to update this. How much heat is invested in this system as it goes from some initial state A to some initial state B? And do I need to update anything more? Yeah, I do. I just want to be consistent. And I don't want to be confusing because this stuff is new. All right, this is going to be T subscript B minus T subscript A. That's good. And I think I'm good to go with the sidebar because this F here, this F is number of degrees of freedom. And hopefully you're nodding your head in agreement that, yeah, this is 5 degrees of freedom because I have if it's diatomic, I have 3 translational plus 2 rotational equals 5. So F equals 5. So that's my sidebar. All right, so let's keep going. Number 4, here's how much heat goes into the system. It equals N times CV, which is 5/2 R plus R times TB minus TA. All right. I guess that's good. And let me just make it clear because, again, all of this is new and overwhelming. Trust me, I know how everything appears overwhelming like this at first. It's like drinking from a fire hose, but this is why you keep doing a little bit every day and it makes it more digestible. This is, again, CV equals F over 2R. Just a little reminder there. That was derived in your green sheet lecture video. Let's go to the next step. Number 5. All right. And I'm going to start subscripting this. How much heat got invested between A and B? It equals N 3.52 moles. Yes. Well, I know 5/2 R plus R is 7/2 R. I know 5/2 plus 1 is 7/2. So I'm just going to call that 7/2 R. Maybe I'll write it like this. That's 7/2 R. 7/2, and I know R is, I'll leave it as 7/2, and I know R is 8.31 joules per mole Kelvin. That looks good. And I know maybe I could have left this as delta T because I know that this is delta T. And I don't know the final or initial temperature, but I do know delta T, which is going to be really important. My question statement says this system increased by 54.2 degrees Celsius. So watch this detail. Watch my incredible attention to detail. I'm going to write that as 54.2 Celsius degrees. And you say, "Oh, Chris, you made a mistake. You should have wrote down degrees Celsius." No, I didn't make a mistake, and the problem statement didn't make a mistake either. The problem statement is solid, but I'm just writing the temperature difference down. The temperature difference was 54.2 Celsius degrees, and then I just need to do dimensional analysis because I hope I end up with joules. Moles here cancel with moles here. Here's a question. Can I cancel? Does Kelvin here cancel with Celsius degree here? The answer is yes, it does, because the little reminder, 1 Kelvin does equal 1 Celsius degree. It's the same step size. The magnitude of the degrees themselves, it's like a ladder. The step size are the same, but 1 Kelvin does not equal 1 Celsius degree. So that's why I do end up with joules. My dimensional analysis looks good. Let's get a number. 3.52 times 3.5. Okay, store alpha A. The dimensional analysis is good. We got the right answer. Store it in your calculator, number 6. This is how much heat. This is how much heat you have to add to your engine or balloon or whatever this is to increase its volume. Why do you want to increase volume? Because increasing volume means you're doing work. This device is doing work for you. 55, 48.9 and some change joules. SICM alpha A. Okay. Done with part A. Moving on to part B. This is part A, done. Part B says, what's the change in internal energy? Okay, so let me erase this. You guys hopefully have an appreciation for how this is really just like Q equals MC delta T, but for a gas. So I'm going to erase this stuff just to clear up some real estate. And now we talk about part B. What is the change in internal energy of this gas as it heats up? And there's much to say about this. There's much to say beyond just, working the formulas. There's much to say beyond just manipulating equations. And let me do that now. This is, you're going to be spending a lot of time on this app right here. Desmos, no, not Desmos, FET gas. So this is a great time just to remind us what internal energy is referring to. Okay, so if I'm sharing the screen, which I am, okay, watch what happens when I specify hold constant. All right, first let me put some gas into this container. Okay, so there's some gas sitting here in a container. I'm going to hold the pressure constant. Ready? Click. Hold the pressure constant. Allow the volume to change. That's what that setting does here. All right, so notice my pressure gauge is sitting there at 17.5 atmospheres. I can change that to kilopascals. All right, now watch what happens when I dump in some heat. Let me make sure. I'm going to dump in some heat. The pressure is going to remain constant. 3, 2, 1. There goes some heat. And look at my volume change. So here's what happens when I add some heat. Here's what happens when I remove some heat. The temperature is changing. The volume is changing, but the pressure remains constant. And what is internal energy? Internal energy is all of the translational and rotational kinetic energy you see here, right on this screen. Let me say that one more time and then write it down. Internal energy is the sum of all of these particles, translational and rotational kinetic energies. So if I really, I guess that's good. Like what happens? Can I change the volume? If I can't drag on that, but all right. So let me just write that down. What I just showed you visually, because you're being asked to solve right now. What is the change in internal energy? So this is the perfect time to write it down after you saw that visual. Step number 7 says internal energy. So I'm not going to write delta E, just internal energy equals the sum of all particles, translational kinetic energies and rotational kinetic energies. So internal energy is a measure of kinetic energy, particle kinetic energy. So this term kinetic energy really is a big deal. Particle kinetic, kinetic energy in general, and specifically the kinetic energy of all of those particles taken in aggregate, rotational and translational. Rotational plus translational. That's what internal energy is. And you're being asked right now to solve it. And it turns out, well, there's a number of expressions. You could say, oh, this is easy. I'm just going to say delta E. I'm going to use first law, which is Q minus W. Great, great. And you're done. You're done. What a simple equation, but you're not done because you don't know what work is. You at this point, you don't know what the work is. So there is an alternative now. There is an alternative introduced in chapter 19, and it starts the alternative derived in chapter 19, and you should totally understand every step of that, starts here. It starts with the first law, and then it adds Q equals NCV delta T, and then it adds ideal gas law, which is PV equals nRT. Anyway, all I'm saying right now, I don't want to relitigate the green sheets or the green sheet lecture videos. I'm saying, hey, if you start with the first law and you remember Q equals NCV delta T, and you remember the ideal gas law, and I shouldn't write positive, that could be confusing. All I'm saying is remember these truths. If you remember these truths and combine them, derive them, you're going to get this expression. Change in internal energy is always equal to NCV delta T. That's a huge point. And you might say, that's nice, Chris, but I don't have constant volume. I have constant pressure. So at this point, you would say, uh-oh, this is not a CV. This is not a constant volume case. It is, in fact, it's a constant pressure case. But it turns out, and I broke a profuse sweat in the lecture video explaining why it turns out for any process you can think of, for any process, change in internal energy is in fact NCV delta T. So you might say, well, why? And the answer is, well, I mean, the cowardly answer is, please check out my chapter 19 lecture video to know why. But for now, I can say, because if the pressure is held constant, it just means I have to add a little more internal energy to affect the same change in volume. So I don't know if that answer, what I just said now will sound crystal clear if it doesn't already, but this is always true. So this is a very frequently used expression, even if it's not a constant volume process, like here, for example. So number 11, the change in internal energy is going to equals N, got it, CV, I'm just going to repeat it. Remember, CV is always F over 2R. I'm just doing this for repetition. Delta T, we know what delta T is. It's given to you. So let's just keep going with this. It's going to equal N, and N was for me, N was equal to 3.52 moles. F over 2, well, it's 5, again, 3 translational kinetic energy degrees of freedom plus 2 rotational kinetic energy degrees of freedom. F over 2 would be 5 over 2, and R is 8.31 joules per mole times Kelvin times delta T, which was 55.2 Celsius degrees. Let's get a number. It's the same dimensional analysis. So 3.52 times 2.5 times 8.31 times 54.2. Okay. 39.63 0.5376 joules. This is change in internal energy. This is part B. Done. And if ever there was a time where it's so easy to get the right number and so hard to see the big picture, the true meaning, this could be it. This is one of those times. But let's not let that happen, because now, check this out, you guys, before we move on to part C. You actually have it standing side by side. This is what you get for with, this was NCP delta T. So this result was brought to you by NCP delta T. This result was brought to you by NCV delta T. And this is a great chance to drive this point home. So what's the difference between NCP delta T and NCV delta T? This is greater. This is greater. And you know why? Because here in this case, when I was holding the pressure constant, the volume was changing and the pressure was changing. So that comes at a greater cost. Here in step 13 here, I'm holding the volume constant. I'm assuming the volume stays the same. So if I hold the volume constant, this amount of heat, adding this amount of heat will increase my internal energy by that much. If I allow the volume to change, I have to dump in some more heat to increase this change in internal energy by the same amount. Let me say that again, because that really does drive the point home very clearly, unless I'm not making sense. But if I am making sense, one more time, this is NCV delta T, this small number here. This number is smaller than this number because here the volume is allowed to change. So because the volume is allowed to change, that means work has to be done. So 5548 equals 3963 plus some amount of work, because some amount of work had to be done here in this case to deal with expanding the volume. Okay, so anyway, I'm breaking a sweat again. Hopefully you'll understand that. If not now, then soon. That's going to be very empowering. Part C says, how much work is done by the guest? Well, that's a timely thing to ask because I just kind of try to yammer through that. All right, so let's do part C. Okay, getting a little bit small, but this is the perfect time to do part C because number 14 wants you to figure out how much work was done. Work equals the dollar sign. How much work was done from thermostat A to thermostat B? And then, this is a job for what I just said. I just went through this. First law says change in internal energy equals Q minus W. We just solved for this. We just solved for change in internal energy, which is here. We got a number on that. We got a number on Q. This came from NCV delta T. This came from NCP delta T in this case. And this is our dollar sign. So look how easy this is. Work. Now we're just in arithmetic land. W equals Q minus change in internal energy equals that SICM A number minus SICM B. And I better indicate this is SICM B. SICM, store in calculator memory location B, and store alpha B. So if I do alpha A minus alpha B, I get the answer. This is the amount of work done, 1585 and some change joules. That's the answer to part C. The work done from A to B. And that really is a great time to write down that number because it's the difference. This is why change in internal energy is always NCV delta T, because if the volume is not held constant, you're going to have to do some work to accomplish the same amount of change in internal energy. All right. Last part. How much of this increased kinetic energy was rotational? That's what it's saying. If you read part D is saying, by how much does the rotational kinetic energy of the gas increase? And I can kind of make short work of this, I think, because number 18 says, what is the change in rotational kinetic energy? That's how I'm going to write it, $sign. The $sign is the change in rotational kinetic energy of the gas. This is what we're after. And then I say, aha, I know there are 5 degrees of freedom. I know there are 5 degrees of freedom. 3 are brought to you by translational kinetic energy, plus another 2 from rotational kinetic energy. 3 plus 2 equals 5. So you know what that means, number 20. So the rotational kinetic energy is basically 2/5 of the internal energy. If I have a diatomic molecule, then 2/5 of that diatomic molecule's kinetic energy is rotational kinetic energy. So then the question is, I'm not after kinetic, I'm after the increase. The change in the rotational kinetic energy is going to be 2/5, 40%, of the change in the system's internal energy. The other 3/5 come from translational kinetic energy. So all I need to do is 2/5 is 0.4, 2/5 is 0.4, and the change in internal energy is just sitting here in calculator memory location B. And that's why if I do 0.4 times alpha B, I get 1585. It's interesting why this number is exactly the same as part C, as the last number, 1585.41 joules. And to be honest, I need to think through that. I need to take a minute, or maybe you need to take a minute, or we need, it'll be interesting to think about why that is the case, because this is the answer to part D, which is, so the question is, why is the change in rotational kinetic energy the same as the work done? That's interesting. So is it coincidence? I think not. But we're done. We're done with this problem. We are completely done with chapter 19, quiz 3. It's now, what time is it? Let's do one more, maybe even take a break halfway through, because breaks are important. Let me get the next quiz available. When 16.6 joules was added as heat to a particular ideal gas, the volume of the gas changed while so it's another. So get out your favorite pen or pencil and let's draw a PV diagram. Dependent variable is P, independent variable is V. You're adding some heat. The volume of the gas increases while the pressure remains constant. So we've seen this is looking familiar. So let's do this. Here's isobaric. Isobaric, I'm starting at some thermodynamic state A, and I'm ending up at some thermodynamic energy state B. Isobaric. And the only way you could accomplish this, the only way you can hold pressure constant and increase volume is if you do add heat. So always think through, always ask, that chain reaction of questions. I know heat has to be added to the system from A to B. The volume of the gas changes from 51.6. So down here, this is 51.6 cubic centimeters, and just my knee-jerk reaction is convert to cubic meters. And then it ends up over here at 83.2 cubic centimeters. Maybe I don't have to convert, but I'm saying I need to be dimensionally consistent. So if ever you ask me or anyone, like, hey, what units do I need to use here? The answer is you need to use the units to be dimensionally consistent. So it sounds like a sidestep, but it's not. So the pressure remains constant. So I know this pressure right here is a constant 0.937 atmospheres. So this is PAB. I'll write it like that. The pressure at A is the same as the pressure at B. So I'll call it PAB. 0.937 pascals. That's given, 0.937 atmospheres. So it's a different unit. But I know how to convert between pascals and atmospheres. This is an ATM. ATM. Question: how much did the internal energy of the gas change? How much, when this happened, when you went from A to B, when you went from A to B, what's the change in internal energy? And based on my inspiring and emotional rant about why change in internal energy is always equal to NCV delta T. And I should note that this was derived. So it's more, there's more to it than me just trying to describe it like a maniac. There's me describing it like a maniac and actually a mathematical derivation. So again, don't sidestep that. All right, so let's get an answer here. Ready? Unless it's not quite so easy, but what's N? I don't know. I do know if the quantity of gas present is 1. All right, so I do know N. Here's N. 1.4 E minus 3. 1.4 E minus 3 moles. That's N. Here's CV. So right now I'm saying, is F equal to 3, which would be a monoatomic gas, or is F equal to 5, which would be a diatomic gas, or is F equal to 6, which would be a polyatomic gas, which we haven't, but we will. So does this talk about whether it's a monoatomic, a diatomic, or polyatomic gas? No. So I'm going to say, So I don't know CV. I don't know enough to know what CV is. So CV delta T. And then I'll start panicking and say, what's CV? Don't know. So then this would be very typical. You just say, okay, well, I'm not going down that path. What about this? Let's try first law. You know why I'm trying first law? Because I can't think of anything else at this point. My first thought really was delta equals NCV delta T, just because I had that on my brain. But I'm going to try the first law. Change in internal energy equals Q minus W. Well, I'm liking this maybe. Well, I like this for the following. Here's Q. I know what Q is. Can I find W? Yeah, I can find W. W is this. Let me draw it on the screen. W is the area under this graph. So what I'm highlighting here in orange, this is W, the area. So that's the amount of work done by this working substance, by this system from A to B. The volume's increasing, the piston's moving up, work is being done because the force is the force and the displacement are in the same direction. So all of this is positive work. Not only is it positive work, but it's a rectangle. It's a rectangle. So let's do that. Ready, set, go. Number 4. Change in internal energy equals Q 16.6 joules minus that rectangle. All right, so that rectangle is going to be length times width. So here's, ready, it's going to be PAB times VB minus VA. And this is VB. This is the volume at state B. This is the volume at state A. So if I want the area of this orange rectangle, it's going to be this dimension that I'm indicating right here. What is that dimension? It's PAB. What is this dimension right here? This dimension is VB minus VA. So that's where I'm getting number 4. So let's do 16.6 joules minus PAB, which is 0.937 atmospheres. And we got to convert it to be dimensionally consistent. I'm going to convert. Here's the conversion factor. 101, 325 pascals, 101,325 pascals per ATM. You don't have to memorize that. That's not something you need to memorize. That's not a derivation. It's just a conversion factor. So all of this is P, and here's delta V. Delta V is going to be, well, technically, all right. It's not delta V, it's VB minus VA. So it's 83.2 minus 51.6, common units, centimeter cube. Don't like that centimeter cube. That's not going to keep me dimensionally consistent. So I'm going to do 1 meter per 100 centimeters. And that whole, there's my conversion factor, but I need to cube it. There you go. And is that done? So let me double check. This is Q, fine, minus all of this is PAB, that side of the width of that rectangle. And all of this is VB minus VA, which is the base of that rectangle. And with the conversion factor, so let's get the right answer and do dimensional analysis. Okay. 13.6. Keep that in memory location. Equals 13.6 and some change. Joules, but dimensional analysis should have done it first. What if I made a mistake? I could have just wasted a bunch of times. ATM cancels with ATM. So from a dimensional point of view, I have joules. So I have joules here. I have joules minus a Pascal times meters cubed is the same as a joule minus a Newton per square meter, because a Pascal is a Newton per square meter, times meter cubed, or joules minus joules. So yeah, I do end up with joules. Okay. Store alpha A. Store alpha A. That's part A. B says, what's find, it's saying find CP and find CV. Okay, so that's what we're done with part A. Part B says, find the molar specific heat of the gas at constant pressure. So part B is asking for the molar specific heat of the gas at constant pressures. And you know what that is? That's the fully descriptive way of saying CP equals $. CP equals $, is part B. Find it. Because, and this will be helpful because we don't know if this is a monoatomic or diatomic or polyatomic. And here's the other thing. What if it's a mix? If it's a mix, then we'll find that out. Number 6. All right. So start with, I know this. I know Q equals NCP delta T. And again, this is just the gas analog to Q equals MC delta T. MC delta T, this is used for liquids and solids. This is used for gases. So it's the very much similar. All right, so solve for CP in that. So number 7 seems straightforward, but is it? All right, so isolate. If I isolate CP, I'm going to get from number 6, I should say, I'm going to get CP equals Q all over N delta T. And I know all of this, I think. Q, let's see, let's do the sanity check. I know the amount of heat added. It's 16.6 joules for my numbers. N is given, and I know delta T. So let's make quick work of that. Which means you're going to have to do the dimensional analysis. 16.6 divided by 0.0014. Oh, I knew it. Don't know delta T. I don't know delta T. So let's keep going. Just when I was ready to take a sip of tea. All right. So, All right. Number 8. Number 8. What's delta T? What is delta T? Ideal gas law? Let's try it. Let's try the ideal gas law. The ideal gas law is saying PV equals nRT. If P is constant, so if P is constant, which once again, I will write it like this. If there is no change in pressure, if delta P equals 0, which means isobaric process, and you were told this pressure remains constant, then I'm gonna write it like this. I'm gonna say P. I'm gonna take the delta of both sides. So this is how I think of it. I'm gonna say delta PV equals delta nRT. I'm taking the delta of both sides. I'm basically just differentiating both sides. If P is constant, then it's just going to be P delta V, because again, P is constant. And I know on the right side, N and R are constant. So N and R can come out of this and there. So this is basically just doing, I'm deltaizing or deltaing or differentiating the ideal gas law knowing what's constant. So there's my answer. I have delta T equals P delta V all over NR. So there, a little bit of a sidestep, but we're back on course because now CP equals Q, let me not write down numbers just yet, over N times delta T. Here's delta T. Delta T is P delta V all over NR. So I can simplify that. You can see N here cancels with N here. So the molar specific heat capacity for this system at constant pressure is Q all over P. I better subscript things here too. PAB delta V. I'll write this because you know what delta V is. Delta V from A to B all over R. Okay, so before we take a break, let me just sanity check this. Number 10 is going to give us the answer to part B, unless there's a mistake. But before, let's see. Q is given. My Q is given as 16.6. Good to go there. PAB is given. For me, PAB is 0.937 atmospheres, but you got to convert. VAB is given. All right, I know all of this. So I'm going to do one more line and then, well, here, let me do this. It's now 10:30. I'll see you guys. Let's do this. See you at 10:39 a.m. But before I run off for 9 minutes, let me just say, just remind you guys, see you at 9:39. But you know everything. In step 10, you know everything. Just remember, you need to convert. I'll just remind you of the little conversions you need to do. Convert from ATM to pascals and convert from cubic centimeters to cubic meters. And everything, all of those conversions were done in part A. So you're good to go. I'll see you guys at 10:39. Very few. No one's done. One person, Dan. Dan is done. So because one person is done, that need to do, we're done as part of that step 4. You need to convert from cubic centimeters to cubic meters. You need to convert from ATM to Pascal. So I'm assuming that's what's taking you a minute or two. But again, feel free. And I'm not saying the window is closed. If you can think of a question to ask me about this problem, later on, that's fine. But I'm going to make the next quiz available because time marches on. And the next quiz is quiz 5. We'll have some time on Thursday to do more of these problems as well. And if I need to extend anything, I can do that. Okay. So chapter 19. It's time to do chapter 19, quiz 5. It's now 10:41. Chapter 19, quiz 5. And chapter 19, quiz 5 is officially available now. Chapter 19, quiz 5. Oof. Bubbly. All right, so let me get rid of my notes. New stuff. New stuff, which again, ideally, everything you hear now would follow what you saw in the lecture video. But what I won't do, I won't assume anything, but I'm not going to go into the truly deep dive lecture video level conversation. But I'll maybe go deeper than I normally do. Okay, so here we have, here we have a polyatomic molecule. That's what I was looking for. Monoatomic, diatomic, and now polyatomic. I'm just cleaning up my chicken scratch. This is me just making sure I remember some key points here. So what I do, I kind of solve this problem ahead of time to make sure I remember, not to get the right number, but to remember the key talking points. All right, so there it is, and I'm sharing. Opening champagne. In a bottle of champagne, the pocket of gas, which is primarily CO2. So let's talk about this champagne bottle. I'm going to redraw that champagne bottle. So here's the opening of the champagne bottle. Here's the neck. And so there's the neck of the champagne bottle, and then it tapers into, okay, good enough. Okay, so here's the champagne bottle, and it's filled with champagne, some liquid. So it's filled up with liquid to say here. So all of this is liquid. This is the liquid part of the champagne. And here's the cork. The cork of the champagne is right here. So it's just sitting there corked like that. Okay. And then between the cork and the champagne itself is our working substance right here. There's this little pocket of gas that's trapped between the liquid and the cover, which is the cork. And this is CO2 gas, CO2, polyatomic. So let's talk about a polyatomic gas. Polyatomic gas, because the C atom, that's one. I have an oxygen atom, that's another one, another oxygen atom, that's another atom. So basically I have 3 atoms. The carbon dioxide is a 3-atom molecule. 1 atom of carbon, 2 atoms of oxygen. A 3-atom molecule, polyatomic, means many atoms, means more than 2. It's polyatomic. So if we were going to go through this degrees of freedom game again, which I will, this is the purpose, this is what we need to do. If I have a coordinate system there, and I'm just going to draw just this blob. Here's a blob. This is a blob of CO2. This is a CO2 molecule. So within this blob, yes, there's 2 oxygens and 1 carbon. And I'm just going to count up to 3 again. All right, so ready? Here's 1 translational, 2 translationals, 3 translationals. Here's number 4. Here's a rotational, rotating about this axis. That's 4. Here's 5. 5 is rotating about this axis, like this. And now I have 6. Here's the 6. 6 is actually rotating about this axis. So let me like that. Like I'm rotating about, I need to rotate about this axis. That's 1 rotational. I need to rotate about this axis. That's 2 rotational. And then here's the difference. I need to rotate about this axis. So I'll draw it like this. All right. So I could call this might be this is my rotating about my y-axis. This could be rotating about my x-axis, and this could be rotating about my z-axis. I didn't have three rotational degrees of freedom with a diatomic molecule, because if I have a diatomic molecule that looks like this, for example, here's a diatomic molecule, one oxygen, another oxygen. Basically, in the world of diatomic molecules, you do not get rotation about that axis. So no rotation here, no theta x. Whereas here I am getting theta x. So I have 1 degree of freedom, 2, 3, 4, 5, 6. So I have F equals, and to be honest, I can't even know, I don't remember off the top of my head if I need this, but I'm just going on this rant. F equals 6 degrees of freedom. All that 6 kinetic energies. And this means there are 6 kinds of kinetic energy that comprise the internal energy. There are 6 kinds of kinetic energy that comprise the internal energy, comprise CO2's internal energy. Okay, so having said all that, let's keep reading. Before you pop the cork, the pressure is 6 atmospheres, which is pretty big. This pressure, P, and I'm going to just say I for initial. The initial pressure, meaning initial, before you pop the cork, is with my numbers 6.06 atmospheres, that's high pressure, because standard atmospheric pressure is 1 atmospheres. So you can see this is very high pressure because you have carbon dioxide gases forming from the bottled champagne, and the pressure is building up. Okay, when the cork is pulled from the bottle, the gas undergoes an adiabatic expansion. So, and you see that right here. The cork is popped. You remove the cork, and all of a sudden, very, very quickly, you get this volume of gas produced. So this is what happens via adiabatic expansion. Adiabatic expansion. Adiabatic means no heat flows into or out of the system. You had this in chapter 18. This was first introduced in chapter 18. Chapter 18 said, for an adiabatic expansion, Q equals 0. No heat enters. No heat enters or leaves the system. No heat enters or leaves the system. Okay, so and there's two ways that an adiabatic process could occur. The first way is you have it perfectly insulated. That's one way. Another way is what we have here. It's not perfectly insulated. The other way is happens really quickly. Happens super fast. And that's what you have here. The cork is basically shot off of this bottle so fast that the gas expands very rapidly, and you have heat does not have an opportunity to enter or leave the gas. Okay, so that's adiabatic. Not the first time you heard this term, but it's the first time we're going to be really applying it. All right, so when things settle down, when the cork is pulled from the bottle, the gas undergoes an adiabatic expansion. And you see it. You see this fog because it's cooling. This is cooling. Adiabatic expansion means it's expanding. And if this gas expands and there's no heat that flows into it to keep the temperature constant, its temperature is going to be decreasing. So the temperature decreases because heat doesn't have a chance to flow into the system or out of. And if the heat is decreasing, it starts to condense. You go from gas to the liquid, it condenses. And that's why you see that fog. Those are like little vapor droplets. So a lot going on in this problem, that is for sure. Okay. So the final pressure here, the gas undergoes an adiabatic expansion until its pressure matches the ambient air pressure of 1 atm. All right, so I'm going to call that my final. I start out at some initial pressure, 6.06 atms. I end up at standard atmospheric pressure because the cork has been popped off the bottle. Assume that the ratio of the molar specific heats is gamma equals 4/3. We'll talk about that. We know the initial pressure of the gas right here. We are given a ton of stuff. This is T initial. What is the temperature at the end of the adiabatic expansion? All right. So again, I'm expecting cooling. I am expecting adiabatic cooling. I am expecting. You see all of these terms in refrigerators and automobiles and human bodies. I am expecting adiabatic cooling. Because, again, thought process. I'm expecting adiabatic cooling because this gas rapidly expanded, which means heat did not have a chance to flow in to maintain the temperature. It cools off, it condenses. What's that final temperature? All right, so here we go. All of this is backstory. Now we actually start solving the problem. So let's solve all of this problem. Number one. Okay. Number one. This is a job. This is a job for the adiabatic. This is a job for the adiabatic pressure volume relationship. Maybe. Pressure volume. This is a job for the adiabatic pressure volume relationship. Maybe. All right, so here's the adiabatic pressure volume relationships. You will go through a very clear, in my humble opinion, derivation to show the following. P initial, or I'll say P1. P1 V1 to the gamma equals P2 V2 to the gamma. This is the adiabatic pressure volume relationship. So introductions are in order. P stands for pressure. So the pressure at something, in fact, let me do this because I'm so used to using A's and B's. Let me not deviate from that. I'm going to just erase this just to be consistent because we're in the introductory phase here. Number two is saying that for the adiabatic pressure volume relationship, this is P subscript A, V subscript A equals to the gamma equals P subscript B, V subscript B. There. Now let me start over with the introductions. This is the pressure at some thermodynamic energy state A. And when I say thermodynamic energy state, you should now completely get it that, yeah, here's a PV diagram. And then maybe you're going from state A to state B. Okay, I get it. I know what that's referring to. V is referring to the volume at state A. Over here on the right side, this is the pressure at state B. This is the volume at state B. And here's something new, gamma. This is the heart of lab 3. So formal introductions are in order. Number 3, gamma. Gamma, it's not V, it's the Greek letter gamma. Gamma is defined, this is a definition, as CP over CV. and you were introduced to CP and CV, and it has a name. This is the molar specific heat capacity ratio. Molar specific heat capacity ratio. And the reason it exists is because it turns out the ratio of CP over CV occurs so often that we just gave it a name, like a Pascal. A Newton per square meter is just, it's easier to say Pascal. It's easier to say gamma than it is CP over CV. All right, so this is it. And this derivation, again, is just waiting for your evaluation. Just can't wait to see what you guys think of when you actually live through the whatever, the 8 or 9 or 6 or 12 steps, can't remember, live through the derivation steps that spit this up. And you need to do that because otherwise you're just an equation operator, which isn't going to really help you on the exam. Okay. Or in life, or as an engineer, as a design engineer or doing analysis. Okay, so here goes. Here goes. What are we solving for? What is the temperature? And then I'm going to say, where's T? Where's temperature? Temperature is my $sign. It says, what's the temperature at the end of this? Where's T final? In fact, where's T final? Where's T initial? So at this point, it's time to make one more adiabatic. One more adiabatic introduction. This is the adiabatic volume temperature introduction. So let me introduce the adiabatic. And we're going to need both of these, it turns out. Adiabatic volume temperature relationship. I mean, and the derivations are not heavy. It all comes from the ideal gas law, the first law, specific heat capacities. So really, I mean, there is a way to look at this where you say, okay, this is eminently understandable. The adiabatic volume temperature relationship says this: T1 V1 to the gamma equals T2 V2 to the gamma. Oh, sorry, to the gamma minus 1. Let me give myself some more space. Gamma minus 1 equals T2 V2 to the gamma minus 1. So once again, brief introductions. And I did it again. I want to use A's and B's. So quick erase. All right, let me try that again. The temperature at energy state A times the volume at thermodynamic energy state A to that exponent is the same as the temperature at thermostate B. I use those terms interchangeably. Energy state and thermodynamic state really mean the same thing, but I'll try to be more consistent. Anyway, good. So I have some pressure right here at thermodynamic energy state A right here. I do know the pressure, the volume, and the temperature with subscripts. At B, same thing. I'm going to know the pressure, the volume, and the temperature. Those are state variables, thermodynamic states. All right. So I'm liking this. I am liking step 6 here because there's my $sign. This is my $sign. B. What happens when I get to state B? That's my $sign. This is what I'm after. So that is what I'm looking for. So let's isolate that. Number 7, TB equals TA times VA over VB to the gamma minus 1. Okay, so number 7 follows directly from number 6. I'll just maybe add a note because you can't just do stuff like that on an exam. You have to talk about isolate TB. Done. So let's now here's another I'm angst-ridden. I'm verklempt. Number 8. Do I know anything about volumes here? Nope. Okay, so what's VA and VB? So once again, I seem to be in a dead end, but I'm going to try the ideal gas law. Try using ideal gas law. Okay, I'm going to try to use the ideal gas law, which step 10, maybe I'm going to go over here just so I don't waste all this open space. Step 10. All right, well, here's the ideal gas law. PV equals nRT. And now with subscripts, that means PA VA equals nRTA. And it also means PB VB equals nRTB. These are all valid. You just have to apply it at a given thermostat. So that's all good. So now let's rewrite. Number 11 says, let's back to number 7. Back to number 7. So here's number 7 again. TB, which is my dollar sign, equals TA, which I have a number on that, so I'm feeling pretty good. Here's VA. All right, VA. All right, let's do some algebra. Here's VA. Here's VB. So here is VA, because again, I'm looking at number 7. VA can be written as this: nRTA over PA. All of that is VA. Here's VB, nRTB all over PB. All right, so that looks pretty messy, but I mean, you can probably see already how that's going to greatly simplify. So let me just, this is my volume at A, which I'm referring to this. Right, so I dealt with VA. Here's VB. This whole thing, thanks to the ideal gas law, is VB. So I need to parentheses and to the gamma minus 1. And there's my answer, but not quite ready because there's more hammering to do on this. You can see some cancellations here. You can see that this NR right here cancels with this NR right here. And then number 12 then evolves into number 13. The temperature at B equals the temperature at A. And here comes the whole cooling process. This is going to be PB TA all over PA TB to the gamma minus 1. Okay, number 14. What's gamma? What's gamma? And the answer is gamma is defined as CP over CV. Now watch it. CP is the molar specific heat capacity at constant pressure. This was shown to be CV plus R. So I have CV plus R all over CV. Let's keep going with this. What's CV? CV was shown to be F over 2R plus R. That's my numerator. My denominator is CV, F over 2R. Got it? And this is polyatomic. Polyatomic. So I went on that long rant that I think I erased. Did I? Yeah. I erased all of that background story on how F equals 6. So this is going to be 6 over 2 because there are 6 degrees of freedom. There are 3 translational kinetic energy degrees of freedom plus 3 rotational degrees of freedom because it's polyatomic. So what is 6 over 2R plus R all over 6 over 2R? And I'm just showing every step in its nauseating detail. This equals 4/3 R. So that is the value of gamma. And you might say, for those of you who were paying attention, You might say, Chris, you just wasted 5 minutes of my life because the problem said, assume the ratio of the molar specific heats is 4/3. If I gave you this problem, I give you a variation of this problem. And one of the variations would be, I'm not going to tell you. I wouldn't tell you that. Oh, in here, it's not 4/3 R because I'll do it like this. It's 4/3 because you can see here all the R's cancel. All right, so that's good. Even though that was given to you, I wouldn't give it to you. You'd have to show that, and it'll be easy. Trust me, guys, all of this gets easy with practice. So now are we ready to get the temperature? Number 15. Number 15, the final temperature equals the initial temperature, TA, times the pressure at B. All right, the pressure at B. Well, B ended up, B is my atmospheric pressure. This is a final pressure. Final P is just 1 atm. Let me check that, right? It just returns to atmospheric pressure, the ambient. So after you pop the cork and this gas rapidly expands, the pressure very quickly returns to atmospheric pressure. It started off at high pressure. This was the initial pressure, was P equals 6.060, 6 times the standard pressure. That's pretty high pressure. This was my initial. Okay, this was my initial temp. And you can see here, here's final temp. So now I have final temp. I need to do a little bit more math, but that's what we're looking at here. All right, so with that in mind, let's continue step 15. TB equals TA times PB times TA all over PA times TB. And gamma minus 1 is going to be 1/3. Not 1/2, 1/3. Gamma minus 1 equals 4/3 minus 1 equals 1/3. So I'm just going to write that 1/3 there. Okay, so, but I have TB living on both sides of my equal sign. So how do I deal with that? I don't know. Any way you want, really. So I'm going to do this. Number 16. You could do logarithms, but I'm going to do this. I'm going to say TB equals TA, and then I'm going to do this. This is just a way to do it. Let me move over here. 16. TB equals TA, nothing changed there. And then here's my way of doing it. PB, P subscript B times T subscript A all over P subscript A. All of that is to the 1/3 times 1 over TB to the 1/3. So then my next little math step would be, you can do this however you want. I'm going to say TB to the 4/3 equals TA, just moving the TBs over to the other side. TA times PB, TA over PA there. All right. So I'm going to keep going just because this might be different-ish type of math, arithmetic, really. All right, so let's keep going. Number 18, because then there's some conversion factors. TB to the 4/3 equals TA. Now, here's something. TA is given as 7.2 degrees Celsius. Do I need to convert that to Kelvin? I think so. So I'm going to convert to Kelvin. 7.2 degrees Celsius. plus 273.1. And I'm gonna comment on all of this. This is TA. This is my temperature at A. This is my starting out temperature. Always or convert. I need to convert from degrees Celsius to Kelvin because all of this is based on ideal gas law. So this adiabatic temperature volume relationship is part of that derivation. And you'll see this. Part of it is the ideal gas law. And as soon as you use the ideal gas law in any derivation, that tells you you've got to use Kelvin because that's the basis for the ideal gas law. All right, so this is my temperature at A after I do my conversions. That's how you do the conversion from Celsius to Kelvin. What's my pressure at B? My pressure at B is ambient, 1 atm. Times my temperature at A. My temperature at A was that 7.2. So there's another A. Well, that's fine. Times 7.2. Probably should have done this all together at the beginning, but that's fine. Plus 273.1. So that's PA/TA all over. I'm sorry, I should have said PB. PBTA, and here's PA. I started off at 6.06 atmospheres. And I guess that's it. All right, and this is Kelvin to the 1/3. All right, so let me go back and comment on all of this. All right. All right, so this is TA, convert. Again, I'm convert from degrees Celsius to Kelvin. Got it. So I'm just going to be paranoid here. There's TA. PB, which is the pressure that I end up at, that was 1 atmosphere. So that is PB, got it. TA was my starting out temperature, just sitting there in that champagne bottle. It started off at probably room temperature or much warmer. So TA right here, this is my starting out temperature. I'm converting once again from degrees Celsius to Kelvin because of the basis of the ideal gas law. So this is TA, fine. And then all over PA, this is my starting out pressure, very high pressure, PA, raised to a power of 1/3. Check, check, check. Okay. Let's get a number on 19. Let me check my time here. Time check. 11:15. This will be good. Oh. Okay, so number 18, number 19, TB to the 4/3. TB to the 4/3 equals, let's get a number. Let's get a number for TB to the 4/3. Yikes. I'm going to do that. I'm going to do that at least one more time. I tend to do calculations twice just to make sure I get the same thing. I do them enough until I get the same answer over and over again. So that is alpha A. Okay. Okay, I got the number twice. Doesn't mean it's right, but got to move on. Number 20. So TB equals TB to the 4/3 TB is, I take TB to the power of 4/3. I mean, you could do this with logs and raise that to a power of 1/3, which means I'm going to take my 1006.17 and raise that to a power of 1/3. When I do that, oh, sorry if I said that wrong. Almost made a catastrophic error. This should be to the 3/4. So I'm take that to the 3/4. So it's like, again, what is 2 to the power of 2, all of that raised to the power of 3? The answer would be it's 2 to the power of 6. So it's just using exponent rules. All right, so I'm going to take my answer. And I always have this kind of conversation to remind me how, to remind me of exponent rules, or again, use natural logs. So I'm going to take that to a power of 0.75. There's my answer, number 21. TB equals 178.65 Kelvin. I'm going to put that in calculator memory location B, because they want you to put the final answer in terms of degrees Celsius. So one last conversion, 22. TB is going to equal 178.65 Kelvin minus 273.1 equals minus 273.1. Negative 94.449, negative 94.449 degrees Celsius. Let me check this out. Did I get that one right from my numbers? Okay, that's good. What a problem. So this is an adiabatic. Adiabatic expansion. Adiabatic expansion means things are cooling down. You can see there's quite the mountain of conversions and algebra. And always a real risk you guys are putting yourself in is if you really focus, you're going to focus on getting the right answer. I get that, which means you're spending an enormous amount of time doing algebra, but don't lose the forest through the trees. Don't lose sight of the big pictures here. So that's it. That's quiz 5. That's pretty good progress, really. And I can stop the lifeline that you see here. All of these ones marked DD, those are the deep dives. So there's a ton of problems here, but in reality, I would argue there aren't that many problems here, you guys, given the fact that the deep dives are giving you the solution to 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. 10 out of 17 solutions are given to you via deep dives. We just did an additional 6 today. Is that right? Yeah. And I think, well, okay. So you can tell, and I think we're going to do some more on once, because I think some of the problems I did today were also deep dives, maybe not. But anyway, here's my point. These deep dives are worth their weight in gold. So if your goal is to get the correct answer as soon as possible, don't use the deep dives. You look them up online. And I showed you how you can find the answers to all of these problems online, but I'm saying don't do that. I'm saying check out these deep dives because they give you the really long explanation that you're going to have to understand if you want to do what, if you want to learn this stuff. If you want to learn this stuff and do well on the exam and put this stuff into practice as an engineer, you're going to need to learn this stuff. And that's what I keep coming back to, like, hey, whatever you do, make sure you check out, like here's a deep dive for one of these prompts. And you can see that it goes into a lot of detail, a lot of good, clean, fun detail. This is not the fast way to get the right answer. It's not the easy way. It's the slow, heavy lifting, hard path to follow, that's the path you have to take. You need to do this because it's difficult. That's why. And then you're going to learn. So that's it. And if you're completely done with me, then you can just drift off.
Wait, Professor, I have a question about quiz 5.
Yeah, let me do this first. Let me make 2, 4, and 5 available. Then give me 1 second to do that. Then we can chat some more. Otherwise, I'll forget. I'm easily sidetracked. 2, 4, and 5. Was it a problem about the solution or just some like logistical problem?
It's just about like I'm like putting in the numbers right, but I'm getting a wrong answer. Like,
okay, then hang on. 2, 4, and 5. Chapter 19, quiz 2. I can make that available until 11:59. That's quiz, no, 11:59 a.m. Okay. Quiz 2 is good to go. Quiz 4. $11:59 a.m. And quiz 5 was 2, 4, and 5. All right, so those 3 quizzes are open until 11:59 a.m. So now let's go back and